We're going to analyze here the stability of the fully implicit method for the diffusion equation. Okay, we already obtained the finite difference representation of this fully implicit method, with pretty much looks the same as the explicit method, but again the only difference is that we have considered in the partial derivative of u with respect to x, the second order partial derivative of u with respect to x, the u values evaluated not at time j as the ones that were considered for the explicit method, but at time j plus 1. But as you're going to see, it's going to have an important consequences for the stability of the method. So, and we are going to analyze the stability using the usual case with Neumann or Fourier analysis. So we're going to substitute the u value evaluated at nj by this expression here. And so that's quite straightforward. Basically, what we have to do is substitute it here. And if you are doing that, this is the expression we do have. So here we're going to simplify as much as possible here. As you can see that everywhere appears this exponential. So we are going to simplify with this exponential here. Okay, as you can see here, everywhere appears this eta function to j. So simplify it with that as well. So it goes away the same way. So the resulting one after considering that simplification is that what we do have, and from here it's quite straightforward to clear an expression for the eta function, and this is what we do have. So once we have obtained that, so our aim is going to analyze if that's the absolute value of this eta function is lower than or equal than 1 or not. And that's pretty easy to do, as the cosine function is a bounded function between 1 and minus 1. You have that this contribution here is going to be always greater than 1. So that basically means that the denominator, it's going to be greater than 0. Because in the case, for example, the maximum value it's going to have corresponds to the cosine, getting the value 1, and in this case you have it's 0. So, but it's always going to be greater or equal than 0. It's going to be positive. Yeah, if it's positive, then you have that the denominator is going to be always greater than 1. If it's going to be greater than 1, then you have that the absolute value of the eta function is going to be always lower or equal than 1 for any delta t and delta space. So what does it mean? That's always is stable. So that's why we're saying that this method, the fully implicit method, is unconditionally stable. However, if you remember, in the explicit method, it was conditionally stable to some relation satisfying delta t and delta x. Okay, but in this case, it's not the case. I mean, here this method is always stable, and this is very comfortable. We don't have to care about what kind of space step you have considered, depending on the time step, and so on and so forth. You don't have to care about that. That makes that method, that implicit method, much safer. And here we just made a little change. Basically, what's the philosophy of that is we're using the information. We are actually using the information from the same step that we want to evaluate. We're using information on the spatial derivative of the time step that we want to calculate. That's why actually that's what makes that method, this implicit method, more stable than the explicit method.